Okay, let's dive right in with a totally mind-boggling number, 99.99999%. That is the exact level of purity required for the raw electronic-grade silicon powering, well, absolutely every digital device in your life right now. I mean, it's an almost unimaginable standard of perfection, right? And the crazy part is, that's literally just the starting line. Welcome to this explainer. Today, we're going to explore the sleek, microscopic, and honestly, highly robotic process of modern semiconductor fabrication. We are unpacking the sheer engineering marvel required to transform a raw rock into the incredibly complex integrated circuits that run our modern world. Here's our manufacturing roadmap for today. We'll start with the perfect silicon crystal. Move inside the automated clean room, talk about building the microscopic city, look at the art of planarization, and finally wrap up with filtering for flawless performance. All right, part one, the perfect silicon crystal, ground zero for chips. To build a microscopic city, you obviously need the ultimate blank canvas, right? So how do we get from raw polycrystalline material to a flawless single crystal foundation? Well, we use the Sochkovsky process. It's the industry standard for creating these massive semiconductor-grade ingots. First, high-purity polysilicon gets loaded into a quartz crucible and heated way past its melting point. We're talking 1414 degrees Celsius using radiofrequency induction or resistive heating. Then, this tiny single crystal seed is placed into the melt. As it's pulled up, incredibly slowly, the silicon actually solidifies around it. Thanks to specialized techniques like automated melt stirring and super controlled cooling, this method gives us ingots with impurity levels as low as 1 part per billion. I mean, dislocation densities are under 1 per square centimeter. That is insanely pure. Once that massive ingot is finally formed, it has to be sliced into thin discs. After going through edge profiling, lapping, which thins the wafer using abrasion, chemical etching to remove any sawing damage, and some really intense polishing, you are left with this. A completely pristine 300mm bare silicon wafer that is totally ready to be transformed. Moving on to part two, inside the automated clean room, the fab environment. So let's step inside the actual manufacturing space, what the industry calls a fab. What's really fascinating here is the sheer level of automation. This is a clean room environment where literally every aspect of production, temperature, power, chemistries, moisture, is tightly controlled. Fabrication can take up to 15 weeks for advanced logic devices, and to pull that off, these facilities rely completely on automated material handling systems. You might notice these robotic tracks overhead. They're constantly transporting wafers from machine to machine in enclosed environments just to ensure absolute precision and safety. But you know, automation just isn't enough. The air itself has to be engineered. To prevent catastrophic microscopic defects on our blank canvas, these fabs use high-efficiency particulate air, or HEPA, filtration systems. Just to give you an idea of the scale we're talking about here, a semiconductor cleanroom is required to be a staggering 100 times cleaner than a hospital operating room. 100 times! Because when you're working at the atomic level, even the tiniest speck of dust is basically a giant boulder. Okay, part three. Building the microscopic city, front-end processing. With our pristine environment locked in and our raw wafers prepped, we can finally begin the intricate construction process. We are quite literally building a microscopic skyscraper city, layer by layer. The crucial starting point here is understanding FOL, or front-end of line processing. This is that foundational phase where we actually engineer the raw wafer itself. Sometimes even before depositing materials, chip makers will introduce a straining step, depositing a variant like silicon germanium. What that does is it actually stretches the silicon's crystal lattice. It's a tiny change, but it significantly improves electronic mobility for the transistors that are going to be built directly into this layer. And then, through highly advanced photolithography, etching, and thin film deposition, our microscopic city starts taking shape. Think of it like construction crews made entirely of gas and plasma using chemical vapor deposition to lay down protective foundations of silicon dioxide. Meanwhile, ion implanters act like microscopic artillery, firing boron ions directly into the silicon near the surface. This acts as a self-aligned implant to form the sources and drains for the transistors. It's just an absolute marvel of physico-chemical engineering. Let's look at part four, the art of planarization, flattening the city. So here we run into a major problem. Just like stacking uneven floors in a high-rise building, stacking multiple microscopic circuit layers creates a really bumpy, non-planar mess that threatens the structural integrity of the entire chip. When you look at this kind of cross-section, you can see how multi-level integrated circuits essentially copy the up and down areas from one level to the next. Every new metal layer just magnifies the bumps of the layer right below it. If you leave that unchecked, this nonplanarity becomes severe. It leads to poor step coverage of deposited films and utterly destroys the depth of focus that high-resolution photolithography tools need to print the next level. To solve this escalating topography problem, the industry relies on a process called CMP, or chemical mechanical planarization. You can basically think of CMP as a microscopic steamroller. It uses a tool with a rotating wafer carrier that presses against a polishing pad, and a highly specific chemical abrasive slurry is dispensed right onto it. This combination, the chemical interaction plus the mechanical polishing, flattens out all those uneven areas. That extends the performance of the lithography tools and allows chipmakers to keep shrinking circuits down to ever smaller nodes.
Which brings us to part 5, filtering for flawless performance, defeating particles.
In manufacturing, it seems like every solution introduces a brand new challenge. While CMP solves our uneven surface problem, the chemical slurry it relies on introduces a deadly new threat to our microscopic city: oversized particles. The CMP slurry contains working microabrasives like alumina, silica, or ceria. But over time, maybe due to temperature changes or excessive shear from pumps, these particles can settle and clump together. They form aggregates, agglomerates, or gels with water trapped inside. In the industry, these are known as large particle counts, or the PSD tail, basically oversized particles greater than 0.5 microns. And if these hit the wafer, they act like boulders, catastrophically scratching the interlevel dielectrics and completely destroying the chip. Defeating these particles requires a highly engineered slurry distribution system with really elegant filtration at 3 specific locations. First up, post-blending open-grade filters make sure no agglomerates break free into the day tank. Second, the distribution loop uses clarifying filters as a sort of roughing stage while the slurry recirculates. And third, the point-of-use filter. This one sits right upstream of the CMP tool, acting as the final, absolute critical guard against any oversized particles right before that slurry hits the wafer. But here's the catch. You can't just use standard filters. If you used typical high-purity chemical filters, they'd actually strip out the beneficial microabrasives that the CMP slurry needs to polish the wafer. So it's a very delicate balancing act. You need a classifying filter with a sharp cutoff at the point of use to stop the PSD tail, but without altering the percent solids of the slurry. On the flip side, the distribution loop needs a clarifying filter. That one has a broad cutoff and higher porosity to reduce pressure drop and minimize fluid shear, because that shear could actually cause more particles to clump up. The visual proof of this filtration mastery is honestly just stunning. Take a look at the difference here. A copper wafer polished with an unfiltered slurry gets absolutely decimated by microscratches and pits from those agglomerated particles. But a wafer polished with properly filtered slurry, using multi-zone graded porosity media, shows this remarkably smooth, nearly defect-free surface. I mean, we are literally looking at the difference between a functioning microprocessor and a completely useless piece of silicon. And that really brings us to the very edge of modern engineering. We start with 99.999999999% pure silicon, we operate in rooms 100 times cleaner than surgical theaters, and we use atomic-level planarization governed by sharp cutoff filtration. But it leaves us with a pretty provocative thought. As we push Moore's law toward the 1 nanometer node and beyond, how on earth will we continue to protect our chips when a single oversized particle is literally larger than the transistors themselves? What happens when we finally reach the absolute physical limits of filtering out defects? It's a huge challenge, but it's one the brightest minds are working on right now. Thank you so much for joining me for this explainer, and keep questioning the technology that surrounds us.